Now when we are ready to author a finishing toolpath, it is wise to check the results of others to see what kind of surface texture you can achieve. If you go to the KTH CNC drive, in the Photos subdirectory, there are result and process photographs of other students' experiences with CNC milling at KTH Architecture School. And we can quickly scroll. And having the intention of making this smooth, we can check out perhaps this one. This is Alistair, who milled a very nice model. I think this is in mahogany. And we can see here that a parallel toolpath was used to achieve a surface which either can be left as it is or very easily sanded down to a completely smooth surface. If we see here, if we click once and see here that this is index 16 plus 17, we can go to the community fees and speeds document, go up to 16, 17, and here we have 16 and 17. It's mahogany wood, and for the finishing toolpath, he used a 4mm in diameter ball end tool. Even though it is not stated here, it was a 3D parallel toolpath, and with a stepover of 2mm, 50% of this given tool diameter. And so as to make sure that the finishing of the model that we intend to mill gets an equally smooth or perhaps even an even smoother surface, we can use a 3D parallel toolpath with perhaps a stepover of 1mm instead of 2mm. 1mm stepover will of course lead to double the time as 2mm stepover would require, but this can be something that we evaluate during the authoring of the toolpath and simulating the results, estimating the time it actually takes to mill. So having decided on the toolpath method, a 3D parallel method, we can choose a tool for it. And if we go to the tool library, we can search for ball end mill, and we see here that those entries, those indices, which are grayed out, they are decommissioned due to being either partially or completely broken. So those we cannot use, of course. But having searched for ball, as in ball end mill here, we can see that we have a 16mm cutting diameter ball end mill, which is far too wide since we use a 10mm flat end mill to define the roughing toolpath. And here it is 16mm as well, and this is 4mm as well. And this was the one that Alistair used. But 4mm in regards to, or in relation to the roughing of a 10mm tool might be a far too large gap. If the gap between the roughing toolpath tool diameter and the finishing toolpath tool diameter is too wide, then the substantially smaller tool the toolpath will reach into cavities which could not have been cleared by the roughing toolpath. And that would mean that the comparatively small diameter of the tool with a very high deflection susceptibility could easily break as it tries to excavate those areas, those cavities, which the roughing toolpath did not reach into. And thus it is a wise move to either use a finishing toolpath diameter of the same or marginally lower diameter as the roughing toolpath. This of course depends on the actual geometry that you're milling, but generally one should be aware of that. Alright, and this one is decommissioned, as well as this one. Here we have 12mm, which is even wider, and these are 16. But here we have, almost at the bottom of the list here, we have index number 26. We have a ball end mill with 8mm cutting diameter in relation to the 10mm diameter of the roughing tool. I think this is a very good candidate for our finishing. And even though the 8mm cutting diameter ball end mill has double the diameter of the tool that was used for Alistair's very nice model here, this change in diameter can be diminished if we define an even smaller stepover. A stepover of 1mm in comparison to the 2mm that we see here even though we use a larger diameter tool, where the ball end mill's radius, half spherical radius, is twice as large, if we use a smaller Stepover, then the result might actually be as smooth or even smoother. So we use this index 26 tool for our finishing toolpath. Let's go into the community fees and speeds document, and we can search here for 26. So the bit used, and it's I think it's easy if you search here for 26, and then you can just scroll along this column and you see immediately if it has been used. Very good, it has been used, although only for MDF before. But we can still copy the properties here of the bit used, the color index, the ball end mill, the 8mm cut diameter, and the number of flutes, 2. We can copy these to a third row here of our own. And one should also, of course, create a third row here. So index 45. And let's copy these 3, I think, as well as this. Let's copy these 4. 1, 2, 3, 4, 5, actually. All right, and now we have a tool, a very good candidate for what we intend to do. And when it comes to spindle speed and feed rate and ship load per tooth, since this is not in MDF, as this tool was previously used with, we cannot use those values given because MDF is much a softer material. So I think here it is prudent that we use as an outset the values that we use for the previous roughing operations with similarly but not identical diameter. So we can perhaps decrease the feed rate a little to perhaps 250. We can increase the spindle speed so as to decrease the ship load per tooth. I can demonstrate this if we copy this beforehand. It will be divided by 0, so I'll first input 13,000, the same as that. And here we have a ship load of 0.01. Then we can increase the spindle speed by a marginal amount, perhaps to 14,000. It will still lead to a change in ship load per tooth, slightly reducing the ship load per tooth, and thus the strain on the bit during engagement with the material during milling. Very good. The maximum depth of cut here we can reduce in a similar manner to perhaps 1 millimeter. And actually this will be per definition, since what we left axially in the settings for the roughing toolpath was exactly 1 millimeter radially. And for this parallel toolpath we will be milling all that is left in one go. We will not have multiple passes. Multiple passes can also be defined if one decides so. But for this particular example, we will use one pass of 1 millimeter. Very good. And there we have those settings defined that we need to input in Fusion 360. Let's go back to Fusion 360. With either setup active or the last toolpath active, we can go to 3D and parallel and add a parallel toolpath. The first thing we should do is select a tool, and the tool index number in the KTH CNC tool library was 26. So we scroll down here to 26 and we double check that these values are corresponding 100% to what we find in the tool library in Google Drive. Very good. We select it, and like previously said, we immediately click it again. We make sure to select the correct one, right click on it, and the renumber tool. And this third tool we will position in the third tool holder in the machine, so we'll make sure that this has a tool number of 3 and renumber. Very good. Now we have 1, 2, 3 tools that are used in this document, and they are all adequately assigned one separate tool number, each corresponding to the tool holder number that is going to be positioned in. Alright, so let's make sure to select the right one here. And then we can input the spindle speed and feed rates that we previously defined, 14,250. So 14,000 RPM and 250 millimeters per minute. This yields a feed per tooth of approximately 0.009, and this is what we have calculated here, 0.009, very good. Having defined the spindle speed and the feed rate, we can go to the second tab, and since this is a 3D parallel toolpath, it's another type of toolpath, so it has slightly different settings. We choose a machining boundary, a selection, we select this edge boundary, and now it is at default tool center on boundary, and this can actually be left at default and we don't need an additional offset. This will make sure that the parallel toolpath does not extend beyond the border. We will manually, with the help of other machines in the workshop, cut away the bottom margin and sand the outside of it, so it does not need to go further out. The finishing toolpath does not need to extend beyond the boundary here. Alright, let's make sure to activate rest machining. Then let's make sure that it's from previous operations. Very good. Having said so, we can go to the third tab, and the retraction heights and clearance heights and the like, they are good at default values. We go to the fourth tab, passes. The tolerance here it's at 1/100th of a millimeter. It can be set to perhaps 1/10th of a millimeter. This is our finishing pass. And here one can define the pass direction. As of now, we leave it at 0 degrees, which means that it will go forward and backwards along the x-axis, but this can be 90 degrees and it will go along the y-axis or any other degrees that you like. Here is a very important setting, it's a stepover. By default, it is at half the diameter of the tool, 50%, but we have said previously that we want to have a really smooth surface, so we can define this as 1 millimeter. That's like 12.5% of the diameter of the tool, and here we can define if it should go one way or both ways along the x-axis here, and we can go both ways. And here one could enable multiple depths, but we do not need to use multiple depths since we only have 1 millimeter of radial stock left by the previous operations. So we can disable this again. We will not leave any stock, this is our final operation. Very good. At linking here, as this is another type of toolpath, we do not have this no engagement feed rate, since the parallel toolpath always engages in material, except when entering and exiting. So having verified that all settings are correct, as well as the other, we have a tool center on boundary, and it's the correct boundary. We have rest machining from previous operation. We have a tolerance of 0.1 millimeter, a pass direction of 0 degrees, a 1 millimeter step over, both directions, no stock to leave. We can click OK. This will generate a toolpath. Very good. As with previous toolpaths, the first thing we should do is simulate it. Position the view here. Zoom in a little. Alright, the first thing you should do here is click on the second tab, Info here, and verify that no collisions are detected. Now it's still calculating, so we'll allow it to finish the calculation. Very good, there are no detected collisions. Then we can just briefly check the machining time here, 8 hours and 23 minutes, and the machining distance. We'll go and come back to this. We'll go back to the display tab here, and we can enable the visibility of the toolpath during the simulation. Can choose an adequate starting speed, and then we can initiate the simulation. We see here, we take note that it enters initially around here, and then it goes along the x-axis, progressing 1 millimeter at a time along the y-axis. And here we see the problem of showing the model in the preview, that sometimes it is showing due to the proximity of the model and the preview stock mesh. So we can just hide the model so as to eliminate that. can increase the speed. Disable the visibility of the toolpath. You can follow it more closely or a little from a distance. And one can really see the smoothness of this parallel toolpath, the results that it yields in comparison to the very noticeable stepping of the roughing toolpath previously made. You can show the toolpath and it looks very much as expected. Alright, and there it is finished. And the first thing we can do, having verified that this is according to our expectations, is to go to the Statistics tab and take note of these values for the machining time and the machining distance and input these in the Google Docs. So having made sure that our correct row is selected, we can input the simulated time, 8 hours equals 8 hours times 60 minutes plus 23 minutes, as well as the toolpath length of 126.165 meters. You can copy the formatting of the above cell with Ctrl-C, Ctrl-Alt-V. And then we can input some information here. Cam 3D parallel, both directions, 1 millimeter, 12.5% Stepover, boundary from chain of edges, tool centered on boundary, and we can add a CNC suffix here so as to make sure that we can add further comments when having milled. Alright, enter. Alright, we can add as well rest machining, no stock to leave. Very good. Going back to Fusion 360, we can right click on the stock, go to stock, save stock, save it as tutorial post finishing stock. Having verified that the simulation is according to our expectations, we can click close and click this button to show the model again. We can go to Rhino, import the post finishing stock. Okay. Let's make sure that there's a new post finishing stock layer here. Position it furthest down. Assign layer. And now we can hide the post roughing as well as the cam. And we can see here what result we can expect as an optimal result if everything goes according to plan. This of course has no frizzying of edges and other things which an actual material situation leads to, but it is a very good representation of an ideal result. We can show the original stock, the post clearance stock, the post roughing stock, and the post finishing stock. And here we have the original model. Right, save this file. Having authored the finishing toolpath, we can save the document. This concludes the 8th part of this tutorial series, authoring a finishing toolpath in Fusion 360.